Yeah, thank you for the introduction. Thank you for the invitation. So I will not go too much on the OEM aspect. So I will show at the end a bit preview what we are doing. I will focus more on instrumentation, on fourth generation light sources. So in the end, so to give you a bit impression what is nowadays possible and also where the future will go. So I'm working at the Swiss light source. I'm responsible for a few beamlines there and for a few instruments as well. And then I will just focus first on the SLS2 upgrade program so that you just know what's going on in the synchrotron world. And then I'll go a bit further towards the instruments. I will just start with some acknowledgements, which are more related to the experimental work I show later on. So in the end, this is mostly from PSI, from Center for Photon Science, from my group and former group member. Then we had a very nice collaboration with Max 4, mostly on having one of our instruments there for a certain time. So there we had already somehow for our instrument a preview of how it's working with a fourth generation light source. And then, yeah, acknowledge for some of the sample systems. SLS2 project. So the SLS had a bigger upgrade project, or has still a bigger upgrade project. So in the end, transforming SLS1 into now a fourth generation light source. So SLS itself started operation, use operation 2001, and then since this it was a quite extremely successful light source, I think. So we had something like 18 beamlines in operation at the end, and at some point after 20 years, more than 20 years, you have to think about the future of a light source. You can do either just an electronics upgrade, small upgrade with the same properties, or you do a proper upgrade. And then we took a decision to do a proper upgrade and transform the third generation synchrotron into fourth generation light source. So in the end, we had then some boundary condition, and one of the big boundary conditions is always a circumference. In the end, you have a given tunnel structure where the machine is located, and then you have to squeeze in a new machine into the existing circumference in the end. With this 288 meter of the SLS1, this is a bit the limit that you can accommodate all the necessary components within the circumference. So all other synchrotrons, for example, also Max 4 and so on, they are more towards 450, 500 meter circumference. So then it's a bit easier to get all the components in. So in the end, the general lattice structure stayed similar. So we kept the same number of straits. We have 12 straits at the SLS. Also the source positions could be maintained, let's say, on the centimeter level. So these parameters stayed the same. The major upgrade was really the magnetic lattice. So one of the important buzzwords is this multi-band achromat approach. So in the end, the number of band magnets in a sector, basically, this is what is important for the emittance, one of the important parameters of a synchrotron. So this scales with the third power, 1 over the third power of number of band magnets. And so we went basically from a 3-band achromat to a 7-band achromat, so that means from 36 to 84 magnets. So this gives then just improvement of factor of about 20-30. Plus then also a more modern machine concept and so on. In addition, we also increased the energy slightly from 2.4 to 2.7 GeV. This sounds small, but the radiated power goes with the fourth power of energy. So that means this is just 60% more photons coming out of the machine, just going from 2.4 to 2.7 GeV. And then for us, the important number is the emittance, and this is the product of the source size and the divergence, or the electron beam size and the divergence. And in the end, for us, from the photon science point of view, this is then more or less like the brilliance with some factors and so on. So that means how many photons and how big the source is, how small the divergence is. So this is what goes into brilliance. And so there, especially in this important number of emittance, we went down from 5,500 picometer radians to 157 picometer radians. So, and this is then a really significant improvement. So typically the coherent flux, which is important for all the techniques, or many of the techniques we are using, went up by at least a factor of 20, 30, at the higher energies even up to 100. So this is now really a significant improvement. So what we obtain now with the new SLS. This was a longer project. So in the end, for us, from the photon science point of view, the important part is start of dark time. So we switched off the machine in end of September 23. And then we had about 1.5 years, so until end of 24, to rip out the old machine and reinstall the new machine. And then we started in January with trying to inject the first beam into the storage ring. So mid of January, we had the first stored beam, and then we were extremely successful. So thanks to our machine group and beam dynamics group, we could ramp up the current to the nominal current by beginning of April. We had already designed current in the machine is 400 milliamps. So this was an extreme smooth, extreme quick start, and also with no bigger, and yet no problems. So even no instabilities, what you typically could observe in these machines. And so we have now already come to this, the first beam lines online. And the idea is to have them towards end of this year. Again, expert use operation at a few beam lines, which is also a good chance. So for all who want to try out something, so we have at the moment no regular proposal system. So this is now more on invitation by the beamline responsibles. So if you also interested in doing some work at the synchrotron, this is now a good chance to somehow slip in with our proposals if you can convince the beamline scientists. So we have then the beamline upgrade itself is then a bit put into phases. So we have this year the phase 1 beamline. So we want to get 12 beamlines running this year, and then the bigger upgrade projects where also major refurbishments of the beamline is ongoing will happen next year, so that we have then by end of next year most of the beamlines back in business. And then also next year we will restart with the regular use operation, and then we will have the first call for proposals in the, I think, March next year for the second half of next year. Just to give you an impression what an upgrade of a synchrotron means. So this was the old SLS, the old storage ring. This was really a few days after we switched off the machine. We just have the nice way we can completely open our tunnel, and then we can take out the old machine, could take out the old machine by crane and so on. And then around Christmas we had more or less empty floor here. And then after Christmas we started to reinstall the machine. So this is some cooling water supplies, what you see there, down there. And then part of the machine we had then already reinstalled the new multi-band achromat, so the 7-band achromat. So in the end, the installation was then finished somewhere end of 24, and then we started with the commissioning, as I said, beginning of this year. Good, so the first beamline switch in operation, we have now one insertion device beamline running, so this is a diffraction beamline, and then in addition we have also a few band magnet beamlines now in operation, and one of them is the Pollux beamline, so one of the microscopy beamline. We just had first light 2 or 3 weeks ago, and now we are starting to get the first images there. So these are the phase 1 beamlines. So for those who are a bit in the tachography business, I think the important one is then the CSAX beamline. So also what Claire showed, the hard X-ray work was done at the CSAX beamline. So there we expect first light in the next month, and then towards end of the year we have then 12 beamlines back and up and running. And perhaps for the later part, the SIM beamline is an interesting one. This is a soft X-ray based, soft X-ray undulator based beamlines, where we will also get a new tachography end station, which is currently still in Sweden. So this is measured data. So just to give you an impression how the photon beam looks like. In the end, it's also the shape of the electron beam. So this was at the PX3 beam line. In the end, there's a KB system which images in the end the beam onto a screen. And there we can really see the photon beam. And there you see we get basically we change from this in the end the height of the beam is not changed that much, but it was quite wide. And now we go more towards a round symmetric beam. And in the end, this is in the end one part of the improvement is the size of the beam, and the second part of the improvement is the divergence of the beam. And this gives in total this factor of about 30 of improvement. Good. So this was just a quick overview of what is ongoing at the SLS2 project. And then I will just present you a few soft X-ray instruments which are extremely interesting for looking at magnetic systems because they cover the L edges and M edges of interesting elements. And in the end, we are I'm using two main techniques. One is they're related. One is scanning transmission X-ray microscopy, and tachography is in the end a special type of scanning transmission X-ray microscopy. In the end, just as overview, what we have as photon techniques on the imaging part. So I will focus on the real space technique, microscopy, and then a special case. In the end, the output is also real space, but in the end, in between, we have the phase retrieval methods to obtain then the real space images. And in addition, as contrast mechanisms, we use the spectroscopy effects. So this is a classical X-ray absorption spectroscopy on one hand, and then also all the dichroism effects, and now also these orbital momentum effects. In the soft X-ray range, we can cover quite a lot of elements. So it starts typically at carbon. So that means we can cover soft matter, carbon, nitrogen, oxygen, so typically all organic material. And then for the magnetism community, especially the transition metals are interesting, so iron, cobalt, nickel. The L edges, and then the K edges of the 4F elements, which are also very interesting for magnetic studies, especially with terbium, dysprosium, neodymium. All these elements are there of interest. Good. So the simpler way of doing microscopy, it's conceptual simpler, is scanning transmission X-ray microscopy. So that means we get our monochromatic beam from the synchrotron, then we focus it down with a Fresnel zone plate to a small spot, and then we raster scan our sample through it, and from this we obtain our images. So the important part is then that we have then a very precise control of the sample position. So this is one of the important things that typically we use laser interferometry in our systems to obtain a very precise control between the zone plate and the sample. And in the end, the spatial resolution is limited by the size of the beam. And in best cases, let's say 10, 15 nanometer is typically what can be routinely, 20 nanometer, routinely achieved in a zone plate based system. So the advantages, it's rather simple technique. So you have a quite easy sample environment. So it's vacuum, but it's just no special requirements. So we can have easily electric fields, magnetic fields, which open then also all the opportunities towards time-resolved studies. I think the main drawback is that the samples have to be X-ray transparent, but there we also developed more techniques to thin down with focused ion beam samples to open up membranes, so that in the early days you were more limited, let's say, to silicon nitride-based sample systems, but we also go now to epitaxial grown systems and then open up membranes, which can be done routinely. So this is so halfway drawback, but we are quite advanced also in the sample preparation techniques there. So in the end, as I said, the limitation comes from the zone plates, so and also from the fabrication capabilities for zone plates, and that's more or less the limit is in the order of, let's say, 5 to 10 nanometer. The main reason is you need quite high aspect ratio, so the zone plate is working. You need very narrow lines, but they have to be tall, and to have a reasonable absorption that they work as diffraction grating, and this in the end limits the resolution of a typical zone plate. So that means in the end the limit can be also transferred in the numerical aperture considerations, but this can be overcome because the same way of looking at numerical aperture is valid on the detector side. So you can also place a detector there and record the diffraction pattern, and if you have a detector large enough or close enough, then you can cover a large diffraction angle, and so then you can recover this spatial information from a spatially resolved detector. And then we come into the tychography regime. So the first approach would be classical CDI, so without scanning the sample and just taking a single diffraction pattern. But this has the disadvantage that it's not that easy to solve the phase problem. So in the end, you lose the phase information on the detector, and then you have to recover it. And then we have the possibility to go towards tychography, and this is then in the end combining the scanning with a spatially resolved detector, and then we scan our sample with in this case, then even rather large beam. So the first attempts were really with a parallel beam, but now we typically use zone plate to focus the beam. But the beam on the sample has typically a few hundred nanometer or micron size, and then we record the diffraction patterns on basically in different areas of the sample, on overlapping areas in the sample, and then we send this into a reconstruction code, so iterative code, and this overlapping constraints, or the constraints from these overlapping points, in the end enable a very robust reconstruction algorithm, so to reliably retrieve the sample information. And the nice thing about tychography is that you do not get only the absorption as we have it in classical Stixon, but you also get the phase information. So it means by using this technique, we even get more information out of our samples. And as, for example, Claire showed beforehand, this phase information for some samples have even more content or can be more interesting than just the absorption. In the soft X-ray range, in the end, if you consider information content of absorption phase is about the same. If you go towards hard X-rays, so as we do at CSAX beamline, let's say 6, 7, 8, 9, 10 kV, then typically there's then more information in the phase than in the absorption. So with the same doses you apply on your samples. So depending on the application, you have really the full information from your sample. So in the end, the requirements, as I said, are similar to a Stixon. In the end, we focus our beam, and then we typically go a bit on the diverging part of our sample, so that we have a beam size of a few hundred nanometer typically. Then we raster scan our sample and record diffraction patterns. And for this, we started already a few years ago a development of a new dedicated end station for soft X-ray tychography applications. And this was then ready, I think, 1 or 2 months before we shut down the SLS. And then we did the first commissioning at the SLS. And then, fortunately, we had a nice collaboration. We have still a nice collaboration with the SoftiMax beamline at Max 4. And then we had the opportunity to bring the end station, which is now sort of portable. So it's a 4-ton thing, but you can easily put it on a truck, bring it to Sweden. And then we installed it in the SoftiMax beamline, and then we started there the commissioning, and it was an even regular use operation. So you could just write proposals at SoftiMax for our end station there. So I think this was an extremely successful collaboration. And perhaps one important thing is, especially in tychography, is always detectors is an important part. So in the end, in hard X-ray, typically we have these single photon counting detectors, and we have the detector group at PSI, which is really a big advantage. And they did some further development so that you can use the single photon counting detectors with special sensor chips, also with soft X-rays. So in the end, we brought the limit, which is typically at, let's say, 2 kV, down to below 500 eV. So that means we can do at 500 eV single photon counting, and this is essential for tachography because it's a noise-free detector and really doing single photon counting. And this is, I think, also part of the success of this story, that we really could go now for this detector. This is then, could go for this detector and, really push the resolution already from the beginning. So in the end, we had it then since the beginning of last year at Max 4, and in 2 weeks we will pack it up and bring it back to the SLS. So the typical first scans are Siemens stars. In the end, what you see in the end is a diffraction pattern when the beam is going basically across this pattern, and then you reconstruct the amplitude and the phase from this test pattern. And the nice thing is immediately we in the end hit the in the Fourier ring correlation the end. So in the end it was really pixel size limited, and this was just from geometry to about 5 nanometer. And in the end, this showed then also the stability of the instrument, because you have to have this precise control of the sample with respect to the beam and so on. And also the high dynamic range of the detector. So all these things were really shown immediately that this works quite well. And I think part of the success is really going to a diffraction limited light source with a high content of coherent light. This is just, then just one example from multiferroic materials. They were just nice test samples in some way, and we are also working since this in my group on these material systems since quite some time. In the end, these are small platelets, so typically of a lateral dimension of 40, 50 nanometer, and a thickness of only 2 nanometers. So they have a quite low absorption, even on resonance. So in the end, when you really compare SEM and then these tachography images and the TM images, especially in the amplitude, they have more or less comparable resolutions, especially SEM. TM is, of course, better in spatial resolution. But the nice thing is then that we can also basically look at magnetic contrast of these systems. So that means we took then 2 images at opposite helicity, and so we could then really nicely isolate also the magnetic contrast from these very thin sample systems. Good. Finally, a bit outlooks. So in the end, together with our detector group, we are also working on improved detector systems. This is, I think, a very important part, this so-called LGAT-IGA, so low gain APD. It's in the end a sensor chip with this internal gain. And the old one it has to be cooled to about -20, -30 degrees C. The old one, we had just more or less a liquid cooling system through the chamber with vibrations and so on, but now we have a Peltier cooled one. So there are also improvements, and they are continuously working on improving also these sensor chips, also to push the energy further down. And just this was a sort of leftover detector initially, and this was a bit larger, so we couldn't approach. So that wasn't this 5 nanometer limitation was just geometrical limitation. With this new detector, we could go already closer, so to let's say 3 nanometer inverse resolution. The next thing, our detector groups like mountains. So the current detector is the IGA, and at the moment they are working on the next generation. It's called Matterhorn, which has a higher count rates and so on. And there we hope to get it the next year. And this is then also a benefit for diffraction limited lights, so with more flux and so on. Then with the new detector, we will, it has also some other nice features towards time resolved measurements. So it's really ideal detector then for the 4th generation light sources. Okay, and as last thing, we started also a bit on optical orbital angular momentum systems. So in the end, these well-known zone plates, and just as last image, these are the probe reconstructions. So the sample was also a Siemens star in the beginning, and we can really nicely reconstruct the probes of these different zone plates. And this was then with a L2 and the L15 zone plate where we tried. So this is one of the next things. We also tried it with magnetic systems, but this is not very conclusive. That's why I don't have the images here. And also then, for us, it's a bit a problem to disentangle really this XMCT contribution and from the ORM contribution. So this is where we really struggle or have to think a bit more on these systems. One thing is also that these ORM zone plates seem to be more robust in the reconstruction. So this is also what we see. So that means even if you're not directly interested in the ORM effects, they might help a little bit the reconstruction algorithms because there's somehow more structure in. So this is also a bit unknown. But these are then things we will, when we have the instrument back, really invest more time into studying all these aspects and effects. Good. Yeah, with this I will conclude. I think, yeah, the important thing is SLS2, the last line, is in commissioning phase. So we are happy for accepting pilot users. So if you're interested in some aspects at some beamlines, contact either me or the beamline scientists. At the moment, I think they're also interested really in getting more experience with the new source and so on. And I think they are happy to have then users which can contribute with interesting science to the commissioning of the beamlines. This, I thank you.